Hello everyone, in this video we're going to be discussing section 10.3, which begins on page 643 of your textbooks, and is entitled Solve Quadratic Equations by Graphing. So what it means to solve an equation is to find solutions, and the particular solutions that we are looking for are when x it crosses the x-axis, when this graph has a y equals 0 value, because according to all these graphs, it's really important to figure out when the ball is going to hit the ground, when you are out of money sort of situation. So we're going to be looking at when our parabolas, our quadratic equations, cross that x-axis, no matter what it looks like. So a quadratic equation is an equation that could be written in the following standard form. We've talked about this before. So standard form is ax squared plus bx plus c, and it equals 0. Where a doesn't equal 0, we do have to have some a value, whether that's 1 or 75, because we need the x squared in order for it to be a quadratic equation. And we've used factoring in the past in order to solve these equations when they're set equal to 0 by factoring and then using the zero product property. So when we've factored in the past, we are actually, setting it equal to 0, we factored and solved for x that way. And that allows us to actually find our x-intercepts. And we can solve by graphing by actually graphing the parabola and then seeing where that parabola, once I've graphed it, hits that x-axis, right? And if we're looking at, an easily factorable equation, you should be able to see that those values are the same. So let's go ahead and look at example 1. First step that we need to do is we need to take that x squared minus 2x equals 3 and put it into standard form. Right? So I need to subtract 3 from both sides. Now that it's in standard form, I can go about graphing it. So I find that the x-intercepts are -1 and 3. And the one way I can do that is I realize, alright, a equals 1, so that makes it really easy to factor. So what are the factors of -3? That'd be a 1 times a -3 or a -1 times a 3. Well, which of the two adds to a -2? That would be this one. So that factors into an x plus 1 times x minus 3 equals 0. And then you use your zero product property, x plus 1 equals 0, and solve to get x equals -1. And x minus 3 equals 0 to get x equals 3 here. And then I get that lovely graph. Alright, so I have my x-intercepts there, and I can do the opposite of b over 2a to find my axis of symmetry and my vertex, and do all of that lovely stuff that we did in the last section. So the solutions of this equation, our original equation, are -1 and 3. And you can check them into the original equation. So when you write it out and you substitute in those values and multiply it out, you should get 2 true statements. Remember, solutions produce true statements. Alright, example 2. Solve this quadratic equation by graphing. Alright, so step 1, put it into standard form. And we do that by subtracting 1 onto both sides. And personal preference here, I see that a is -1, and I don't particularly care for that. So I would divide every single term by -1 and switch all my signs. Alright, which that would result in y equals x squared minus 2x plus 1. Alright, it'd be a slightly different equation, but it would be an equivalent graph. Alright, so once I go about graphing it, finding your axis of symmetry, and then plotting the points and connecting the dots, making sure you know it opens up or down, all of that long checklist from last section, you would find that the x-intercept is actually your vertex at x equals 1. And so the solution is 1, x equals 1. And you would double check that by substituting that in and getting a true statement. Alright, here in example 3, I need to get it into standard form, so I write my original equation, and I subtract 4x both sides. And in this particular example, example 3 is our first example, where I can't actually factor this to figure it out, because I'd get 1 times 7, or negative 1 times negative 7, and neither of those adds to a negative 4. So I cannot actually factor this one and check it that way. So I have to go about it by doing the opposite of b over 2a to find your axis of symmetry and the x value of your vertex. Alright, so this graph actually doesn't have any x-intercepts. So if you look at the graph to the right, you would see that it opens up and it's already above this x-axis. So there are no x-intercepts because it doesn't cross the x-axis anywhere. So this would be what is called no solution. Alright, so here's a couple of guided practice. See if you can factor it and find the x-intercepts that way, which are going to help you graph it, or graph it from standard form using your axis of symmetry, which is going to help you find your vertex, and then using a table. Alright, so here in this key concept box, we have a couple of nice hints for us. A quadratic equation has 2 solutions if the graph of its related function has 2 x-intercepts. A quadratic equation has 1 solution if the graph related has 1 x-intercept. So it only touches. It doesn't go through multiple times, it just touches it. And then there's no real solution to the quadratic equation if there are no x-intercepts. So finding the zeros. Because a zero of a function is an x-intercept of a function's graph, you can use the function's graph to find the zeros. So find the zeros of f of x equals x squared plus 6x minus 7. Another way that you can find the zeros of the function is by factoring, which we've already discussed. So you can go about this factoring process and use your zero product property to solve. So here I come out to 2 solutions. So the way that they go about it is they graph it, and then they see where they cross the x-axis, which that would be at negative 7 and 1. So the x-intercepts are negative 7 and 1, which means the zeros, or the solutions, of the function are negative 7 and 1. And you can always check by substituting negative 7, 1 into the original equation. So f of negative 7 comes out to 0, so that one works. And f of 1 comes out to 0, so that one works as well. Alright, so we're looking for true statements, or when we substitute in our x-intercepts, I should come out to 0 for y, because that means it lies on the x-axis, which means y equals 0. Alright, so approximating the zeros. The zeros of a function aren't always necessarily those integers that I've seen in the last couple of examples. So to approximate the zeros, look at the signs of the function values. If 2 function values have opposite signs, then the 0 falls between the x values that correspond. So let's go ahead and look at an example and figure out what that means. Approximate the zeros of f of x equals x squared plus 4x plus 1 to the nearest tenth. Alright, so we're going to be messing with decimals, and we're going to want to round this one to the 10th. So, I graph my quadratic function, I graph my parabola, x squared plus 4x plus 1, and there are going to be two x-intercepts. One, you can see, is approximately between -4 and -3, and another's between -1 and 0. But I can't really approximate that too much by eye. Alright, so there's the graph, and you can kind of see here, here's -3 and -4, so you know you have 1 right there, and here is -1 and 0, so you know you have an x-intercept there. So, make a table of values between -4 and -3, and 0 and -1, using an increment of, we're supposed to round to the nearest tenth, so we might as well use increments of tenths. Okay, so here is my table of values here from -3 to -4. So what we were looking for was when those signs changed. So keep in mind the y value we're looking for is 0. So we're looking somewhere between, you know, a negative and a positive number. And we've got that -3.7 highlighted because that is the closest x value that produces a y value closest to 0. And then we do it again for the 0 to -1. And we can see that yet again I get some values that are really close to 0, and I'm choosing the x value that it is closest. And another way to interpret the function values, the function value that is closest to 0 indicates the x value that best approximates the 0 of a function. Alright, so in both of those tables, the function value closest to 0 is about -0.11. So the zeros are approximately -3.7 and -0.3. So why don't you try out these guided practice, graph them. At this point, you can, use your graphing calculator or go to desmos.com for these problems in particular. And then you need to write out a chart to approximate those x-intercepts. Alright, here in example 6, an athlete throws a shot put with an initial vertical velocity of 40 feet per second as shown. Alright, so it's being released at a height of about 6.5 feet. A, write an equation that models the height and feet of the shot put as a function of time t after it is thrown, and then B, we're going to use the equation to find the time that the shot put is in the air. Alright, so theoretically speaking, the longer the shot put's in the air, the longer the throw is going to be. Alright, so here is the initial vertical velocity using the vertical motion model. Alright, so this equation we've used over, the past chapter. It hasn't gone away. And we substitute in the values. So 6.5 is our starting height, and 40 is the starting velocity, the initial velocity. And so that gives us our lovely equation. And then B, the shot put, lands when h equals 0. So when the height equals 0, it hits the ground. So we need to set the entire equation equal to 0, and then solve for t. So to solve the equation, we use a graphing calculator, or we go to Desmos. So I'm going to go ahead and pull up Desmos real quick, for those of us that don't have graphing calculators. So here I've typed in my equation. I used y equals. Instead I could use h equals. Doesn't really matter. So I'm going to go ahead and zoom out so that you do see it is a parabola. I could go in the top right here to mess with the different settings. I can see that when I zoom in, I'm looking at somewhere between, I don't know, we can say 0 and 10 for the x, and 0 and 40 for the y. Alright, so I'll go ahead and do that. So I'll do 0 and 10 for the x, and then 0 and 40 for the y, so that I get just a better picture of it. Okay, so I'm wondering after how long is, it going to hit the ground. So I see here that I have two x-intercepts. One's at negative 0.153, which doesn't make sense because I can't go back in time. Alright, I start out at 6.5 feet, and I see that shot put went up, and then after about 2.653 seconds, it hits the ground. So I go back to my problem, and I can use my graphing calculator as well by going into the y equals and then typing in that equation as well. Alright, and then I look at those t-intercepts, or we typically call them x-intercepts. So after about 2.6 seconds, this is about what your graphing calculator would look like if you type that in. So, guided practice number 6. What if, in example 6, suppose the initial vertical velocity was 30 feet per second? Find the time that the shot put was in the air. Alright, so here is our concept summary. Solutions of an equation. I can, the other words for that. A solution is something that produces a true statement. Alright, for these quadratic functions, they're also called x-intercepts, or zeros of a function. Alright, that's when y equals 0, or when it crosses the x-axis. So we can go about solving this by graphing it and seeing where it crosses the x-axis, or by factoring. Factoring is definitely an easier approach than having to go through the entire graphing process. However, sometimes graphing is our only option. Alright, so if you guys have any questions, always feel free to email me and ask, or check in during the online office hours. I look forward to hearing from you.